Physics lab number 5, the Make Your Own Lab. Today I'm going to be deciding to work on projectile modeling. So the question I wanted to answer was, can football players throw a football farther indoors or outdoors? So essentially the goal of this lab is to observe how projectile motion works in both closed and open scenarios. So I'm going to use a closed script model to track and predict motion. Then I'm going to compare it to the non-closed scenario where drag exists and discover differences in motion behavior between the two graphs. So some important physics concepts that we're going to be going over in this lab is first Newton's second law of motion, which basically just states the rate at which momentum of an object changes is equal to the net force acting on the object. So if there's no net force, then the change in momentum is zero. But if there is, then slowly the momentum will change either for better or for worse. So some of the forces in this lab are the force of gravity, which always acts on Earth, and then the drag force, which is going to appear in an outdoor scenario because there's going to very much be air acting against the football. Also, something important to remember is that force is dependent on x and y components, because in this case, the ball is being thrown at an angle, so there's force in the x direction and in the y direction in these scenarios for drag. So it's important to watch out for that, using it based off angle theta. Also, we're going to be going over the momentum update formula, which basically is just going to tell us how momentum changes as time moves forward, which is going to be very important for the drag component velocity and for our x component velocity. And as you can see here, our position will also change dependently based on our essentially momentum and then how much we make our delta t. So the procedure I'm going to use for this is I'm going to construct a closed script model of a closed system using projectile motion with no drag, get the velocity and position data, then build a graph. Then I'm going to make another model of an open system that includes drag force, get the velocity and position from that, build another graph, then I'm going to compare the two graphs to see which one can actually travel farther. So some assumptions I made for this lab was that the system was football on Earth, so everything's all together in the first scenario. It's a closed system. The surroundings in the first are none, but in the second one, the surroundings would be just the air because there is an outer force acting on the system. The football mass I assume to be just 0.01 kilograms, typo over here, but the F net after the ball is thrown should be 0 except for gravity, but F net is the drag force and gravity after it's thrown in the second scenario. The starting velocity also is 10 meters per second, which I calculated from Google Sheets. So this was the code for the indoor projectile motion, and as you can see, it basically just starts the initial position vector, and I just make a base for the ball to travel on, which models a football field. Then over here, I used 45 degrees because that's the optimal angle for throwing a football. Then as you can see down here, as we get closer, this is the iteration procedure where basically finds the force, then it finds the momentum, then it finds the position based off that, and then I output all the data below. This is what it looked like indoors as the trajectory. Then for the second one, I constructed pretty much a similar model, but instead I used the drag components, which basically just incorporate a few values such as theta, the mass, rho, which is a constant, the radius of the sphere, the circumference of the sphere, and then I calculate the area based off that, as that's all part of drag. Then in the next case, you're going to see I use the iteration force vector down here, and then out here it's going to output the data below. So here's just a side-by-side straight away of what it looks like. As you can see, this is the one with drag, this is no drag, so there's a clear difference in how far they can both travel. This is what it looks like on a graphical view of the x versus y positions, and as you can see, there's a difference. This tells us the difference in height left to travel between the indoor versus outdoor scenario was there's a whole extra, essentially 0.5 meters left before it hits the ground. So definitely throwing it indoors allows it to travel farther, based on the Google Sheets graph I got here. So that is something key to know, so we essentially answered our question using that. So basically, we now know that clearly the ball thrown indoors travels farther over the same amount of time. An optimal angle thrown for a football is 45 degrees after several test runs. Drag force is dependent on several factors, such as the mass, velocity, and surface area, because as I changed it, drag wasn't as big of a component before. Also, we now know Haynes King can throw a football farther in a closed stadium, so let's hope we start throwing more indoors. So just some sources of error for this lab was that the scenario was based on a small mass to account for drag. In reality, football is much heavier. Also assumed the football to be a sphere when in reality it's cone shape, which would minimize drag. And then also the iteration is based on delta t, which isn't perfect as it should be close to 0. Thank you for listening to the lab. Hope you enjoyed it.